Hello everyone and welcome to this sixth video that will be part of a series about abstract algebra. So in this video, as promised in the last one, we would look at some examples of subgroups. So as well as give some other very important definitions that we will use throughout this video series. So for the first example, let's look at the special linear group that we presented in the earlier videos. So the special linear group, as we probably remember, we defined the special linear group and we proved that it was a group for the particular case of SL2R. So basically the set of 2 by 2 matrices A, B, C, D with real entries with determinant equal to 1. So one determinant 2 by 2 real matrices. So it turns out that this group here is a subgroup of the general linear group. And well, to prove this, we don't actually need to use one of the subgroup tests we used earlier, because we actually just proved in the earlier videos that SL2R is a group in its own right. And being a group in its own right, and being of course a subset of the general linear group, makes it a group, of course. So it is of course a longer way to prove that something is a group and that something is a subgroup, and of course it is not convenient in most cases. So now let's consider the group of 2 by 2 matrices with integer entries under addition. So this of course forms a group, and it's very, very easy to check. And now let's consider the following subset of this group, that is the set of 2 by 2 matrices, of course with integer coefficients, such that their sum is 0. So now we asked ourselves, is this a group? So to prove this, we can use one of the two subgroup tests that we proved in the last video, but we will use the second one that allows us to check that H is actually a subgroup by just checking if two elements are in this set. In particular, we check that if A and B are in H, then A plus B is in H. Let's see if that is the case. So suppose we have A, that is A, B, C, D, and then we have B, that is A prime, B prime, C prime, D prime, in H, of course. Then what we know is, since they are in H, these things satisfy the following equalities. So A plus B plus C plus D is equal to 0, and A prime plus B prime plus C prime plus D prime is equal to 0. Okay, but now summing these two yields the following, and regrouping some terms together yields the following: A plus A prime plus B prime plus C prime plus D prime. And all of this is equal to 0. But notice that now what this implies is that the matrix A plus A prime, B plus B prime, C plus C prime, D prime is in H. Yes, we called it H. So this shows that it is closed. Second thing that we have to check in order for H to be a subgroup is that for all matrices A in H, we will ideally want the additive inverse of such matrix to be in H. But how can we check this? So if A is in H, then denoting A by A, B, C, D, then we know that A plus B plus C plus D is equal to 0. Well, negating this, on the right hand side, negating 0 just yields 0, and on the left hand side, this yields minus A, minus B, minus C, minus D. Okay, but this just implies that the matrix given by minus A, minus B, minus C, minus D is an element of H. In other words, H is a subgroup under addition of the group of integer 2 by 2 matrices under addition. So we have proved this fact. And now, as another example, which we could call a counterexample, even though we will see why, let's not spoil that for now, let's consider the subset of the 2 by 2 matrices with integer entries, such that A plus B plus C plus D is equal to K, where K is a positive integer not equal to 0. So now what we want to ask is it true that this is a subgroup? So let's see. The first thing that we want to check is that, well, if we have A in V, is it true that minus A is in V? Well, let's see. So if A is in V, this implies that A plus B plus C plus D is equal to K. But negating this yields that minus A plus minus B plus minus C plus minus D is equal to minus K. And being that K is not equal to 0, this implies the inverse of the matrix A is not in V, and thus V is not a subgroup that we can denote in this way. So V is not a subgroup of, under addition, of course. So these were two examples. So we talked about the special and general linear group earlier, and well, let's just call this expansion maybe. But it is possible to expand it a little bit on that point. In particular, we can extend, of course, the notions of general linear groups and special linear groups not only to 2x2 matrices, but actually to n×n matrices generally. And also, we can not only restrict to the real numbers, but in general, and we will see what these things are in future, to fields. So we can consider, and I think you're familiar maybe with the complex numbers, we can also consider n×n complex matrices. We can consider the general linear group and a special linear group of n×n complex matrices, and we can do it with other fields. For now, let's not mention other fields to maybe just not confuse the viewer and wait for when we will actually introduce them. Proving that these things are groups, it's really not that more difficult conceptually, just requires a little bit more linear algebra, so we will avoid doing that also to not make this video too much computationally heavy. So now with this said, let's go back to a little bit of theory and let's prove some other results. In particular, we will prove this following theorem, that is another, we could say, subgroup test that allow us to speed up a little bit of verifications that or whether things are subgroups or not for finite, so we're gonna call it test for finite subgroups. So in what does it say? Well, it says that if we have a group G, so given a group G, then given a non-empty, so a non-empty subset of G, a non-empty finite subset of G, and if H is closed under the same operation with respect to which G forms a group, then H is a subgroup of G. So let's prove this. So we know that H is a finite subset of G, and it is closed with respect to the same operation with respect to which G forms a group. So now we just follow in the following manner. We take an element of H. So we now have two cases actually. So the first one is that A is the identity. So if A is the identity, then we're just gonna have that A will be the inverse of itself, of course, and trivial, we will have that A to the minus 1 is an element of H, verifying what we wanted to verify. If that's not the case, on the other hand, we will actually consider the following series of, well, products. So we consider A, then A squared, then A cubed, then dot 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 dot, and so on and so forth. Well, but we know that this set being indecised, so by countability argument, we could say there's a bijection, okay, happening with the natural numbers, would imply that its cardinality is, of course, countably infinite. But we suppose that H was finite. So what will this imply? It will imply that actually only a finite amount of these values are actually distinct. So for infinite values, we will actually have that they're the same. So we will have that in general, we can find values. So for example, we will have that for m and n that are like powers of these succession of numbers, we will have that a to the m will be equal to a to the n. Without loss of generality, we can suppose that m is greater than n. And what will this imply? This will imply that a to the m minus n is equal to the identity. But now, from this we can just, well, but from this equation, then it's very simple to understand that the inverse of a will just be a to the m minus n minus 1. And so with this, we have concluded our proof of this fact. So let us now prove some more interesting facts about abelian groups. In particular, we're going to prove that G being abelian is logically equivalent as having the following property. In particular, a times b to the n is equal to a to the n times b to the n. So let's prove it. So let's start with the forward direction. And in particular, we know that G is abelian. So for any A and B and C, in G, then we will have A times B is equal to B times A. Okay, but now let's consider the product A times B to the n. Let's proceed by induction. So we will start with the base case, n equals 2. So for n equals 2, we'll have A times B squared. Oh, but what is that? That's A times B times A times B, but A times B is equal to B times A, so we'll have A times B times B times A. But that is just A times B squared times A. But now again, using that, Using again the commutative property of abelian groups, we will have that this is equal to a squared times b squared, and we have got the proof for the base case. So now let's for the induction hypothesis, suppose that this works for an time, and let's suppose that this works for a general n equal to k. So I'm going to say that for k, a times b to the k is equal to a to the k times b to the k. Okay, now if we have a times b to the k plus 1, let's see what happens. So a times b to the k plus 1, this is just a times b to the k times a times b. But this is just a times a to the k, b to the k times a times b. And now again, using the commutativity property, we will have that this is equal to a times k, bk plus 1, a. And this is again, it's just, again, switching these two, a to the k plus 1, b to the k plus 1. And so we have proven the forward direction. For the reverse direction now, I want to just note that if we have, now for the reverse direction, it is actually really simple. So we know that this holds for all positive integers n. Let us now pick two in particular. And what we will get is that a times b squared is equal to a squared times b squared. But writing this in a more expanded manner, we will get a times b is equal to actually a times b times b. Okay, but now multiply, we know that G is a group, and actually we should have said that here G is a group, because actually I should have specified that let G be a group, then G is abelian if and only if this is true, because I mean, of course, we kind of assumed we had a multiplication structure just by stating this, but it was not clear that it was actually a group. So if we want to be like super precise, but so we know that being G a group, we have inverse elements for A and B. So multiplying both sides by b to the minus 1 on the right yields a times b times a times b times b to the minus 1 is equal to a times b, or b times b to the minus 1 is the identity, and the identity times everything is just the thing it was multiplied by, so we get this. And here again, using associativity, we can say a times b to the minus 1, but this is the identity, and this just simplifies to a times b times a. Now multiplying everything by a to the minus 1 on the left, similarly, just yields a times a to the minus 1 times a times b times a is equal to a to the minus 1 a b. But this, again, regrouping these things together, since they're equal to the identity, just yields b times a is equal to a times b. In other words, G is abelian. And so we have concluded our proof. So with this said, we are now pretty much done with these more basic proofs about properties of groups, and we are ready to introduce some new notions that are quite important. So the first one is that of a, well, we gave it in the previous videos too, but let's a little bit focus a little bit more on this definition. Let's give it strictly, and that is of a order of an element. So given G, small g, in a group G, we say that the order of G is equal to n, or just say, we can also denote it like this, if G to the n is equal to the identity. So this is just the definition of order. Another very important definition that we will give is that of a cyclic subgroup of a group generated by one of its elements. So we're going to say cyclic subgroup generated by small g. So again, as before, let G be an element, let small g be an element of a group G. Then we call the cyclic subgroup of G generated by small g, and we denote it like this with these brackets that vaguely look like the expectation value calculations you see in quantum mechanics, maybe if you have a physics background, but just like this. And it is just, as I said, it's just the following definition. So it's just the integer powers of the following element, of the element G in this group G. So now what we want to assert, so in fact an assertion that we will make, is that for any G in G, its cyclic subgroup, this justifies what we call it cyclic subgroup generated by G, is a subgroup of G. In other words, in symbolic notation, we can denote it as such. So let's prove it. It's actually quite simple. So in order to prove it, we can use one of the subgroup tests we used. Let's use the second one. That is a two-step subgroup test. So for the first thing, let's suppose we have A and B in the in this set. Then we will have that there exist M and L in the integers, such that A is equal to G to the M, and B is equal to G to the L. What we will get from this is that A times B will just be equal to G to the M plus L, which is still an element of G. And so we have closure. So now the last thing that we want to prove is the existence of an inverse for each element of this Langle G wrangle, if you want to use like LaTeX notation. So let's not call it subgroup yet until we have proven it. So if we have A in this set, then we will have that as before. A will be equal to G to the M tilde, where M tilde is an integer. Okay, but then its inverse A to the minus 1 is just given by G to the minus M tilde, which is still, of course, an integer. And so by this, we have proven that this is actually a subgroup, and we call this the cyclic subgroup generated by G. So let's look at some examples of cyclic subgroups generated by some elements. So for example, we could take the dihedral group, maybe D4. So let's look at D4, which is the symmetries of a square. So what if we ask what is the, so remember R is a 90 degrees counterclockwise rotation. So what if we ask what is the subgroup generated by this rotation? Well, let's think about it. It's the powers of this rotation, and we have seen in the other videos what these powers are. It is just the identity, which is the identity rotation, just keeps everything in place. Then R squared, and R cubed, and this is it. This is a subgroup of D4. So now what if we ask, on the other hand, what is the subgroup generated by maybe a reflection, maybe the S, the one that we call the S? Well, since S has order 2, and we will prove in the next video maybe the relationship between the cyclic subgroup generated by an element and its order, but for now let's not talk about it. We'll have that this will just trivially be S and the identity. And this is again a subgroup of D4. Another thing that we can notice is that this is actually valid for any group. What is the cyclic subgroup generated by the identity? It is the identity only. And this is a subgroup of D4. This is actually a subgroup. In fact, it trivially has all the requirements in order to be a group. It satisfies all the group axioms, trivially, being just the identity. And this is often called the trivial subgroup. For this reason. So now let's move to some other examples. Consider a multiplicative group modulo n U8 that is given by 1, then 3, 5, 7. And let's consider maybe the subgroup generated by 7. So let's see. 7 squared is 49, which is congruent to 1 mod 8, meaning that 7 has order 2, and thus the subgroup generated by 7 is just 7 and 1, which is a subgroup of U8. So now let's consider, well, 1, as we saw earlier, is just 1. Then let's see 3. So 3 squared is just 1 mod 8, meaning that, again, the subgroup generated by 3 is just 3 and 1. And let's see 5. Well, 5 squared is just 25, which is congruent to 1 mod 8. Why? Because, well, it is 24 plus 1. And so for this reason, the subgroup generated by 5 is also 5 and 1. So you can try and maybe work with other example. So you can try and make some other examples yourself. Actually, as an exercise, you can try and maybe consider U10, so the group U10 under multiplication mod 10, and find the cyclic subgroups generated by all of its elements. So this could be also a good exercise in order to basically get accustomed to this idea. So another important definition that we have to give is that of a cyclic group, because this will come, we will study this category of groups pretty intensively in the next videos. And what is a cyclic group? Well, we say that G is cyclic if given G, small g in G, we have that G is equal to the cyclic cross subgroup generated by G. In other words, G is generated by one of its elements. So an example, immediate example of this of a cyclic subgroup is the integers under addition. Why? Because integers under addition are actually generated by 1, because the cyclic subgroup generated by 1 is just defined as n times 1, where n is an integer, and trivially this spans just all the integers. And so now let us conclude this video with two last important ideas, and that is the idea of a centralizer and the idea of a center. So let's start with a center of a group. So we say that, well, given a group G, we call the center of G, and we denote it by Z of G. It is just the set. It is just the collection of all elements small g in G, such that G times X is equal to X times G for all X in G. So in other words, it's all the elements of G that commute with all the other ones. So in order to prove it, we again use one of the subgroup tests that we proved in the last video. So for the first property we want to check, let's see if given an element of ZG, actually two elements, maybe G and G tilde in ZG, then we will ideally want that the product still lies in the centralizer. So it is closed. Let's see if it is closed. So since G and G tilde both are in the centralizer, we know that G times X is equal to X times G, and also J tilde X is equal to X J tilde for all X in G. Well, now let's consider G tilde times X. Well, by using associativity, we have that this is equal to J times J tilde times X. But now, J tilde times X is nothing but X times J tilde, since J tilde is in the center. But now, again using associativity, we have that this is equal to J times X first and then J tilde. But J times X is the same as X times J. And so we have that this is just X times J tilde. And looking at these two sides of the equation, we have concluded that if J and J tilde are elements of the center, then J times J tilde is also an element of the center. So now for the second property that we want to check, namely if there's an inverse for each element and it lies in the same set, let's consider again an element G, small g. Well then, we have that J times X is equal to X times G. Now multiplying both sides by J to the minus 1 on the left will yield X is equal to J to the minus 1 X times G. And now multiplying both sides by J to the minus 1 on the right will yield X times J to the minus 1 is equal to G to the minus 1 times X. And this implies that J to the minus 1, that G to the minus 1 is in the center. And so this concludes the proof. So now, before we mention another important idea, and that is the idea of a centralizer. This is very similar to the idea of center. And in particular, a centralizer, however, is referred to an element of a group, not to the whole group itself. In particular, if we have an element small g of a group G, we call the centralizer of such element, and we denote it with a big C, C of G, the set of all elements of the group X in G, such that J times X is equal to X times G, so all elements of G that commute with small g. So this is the definition of a centralizer. And another fact that we want to prove is that the centralizer for any small g in G, the centralizer of G is a subgroup of G. And the proof is really similar to the one we gave above, so we'll just repeat it quickly. So again, if we have an element X in the centralizer, then we have that J times X is equal to X times G. But now we're multiplying both sides by X to the minus 1 on the right first yields the following, and multiplying both sides by X to the minus 1 on the left yields X to the minus 1 times G is equal to G times X to the minus 1. And this implies that X to the minus 1 is in the centralizer. So this is for the first property. For the second property I want to check in order to establish that CG is a subgroup of G, is that given X and Y in the centralizer, we ideally want that their product should be in the centralizer. Let's see. So we again here consider X times Y times G, and then using associativity, X times Y times J, and now using the property that y has being an element of the centralizer is equal to x times g, j, x times g times y, and then again this is equal to g, j, this is equal to g times x times y, and this concludes the proof. So yes, the centralizer is a subgroup of a group. So with this said, I think we covered all we needed to cover in this video, and in the next video we will move to the next very important topic in abstract algebra, and that is the topic of cyclic groups. And in fact, we said already that we will cover them more in depth in the future. So with this said, I think we can now conclude this video here.